Okay, so um, homework D2 has been posted, and the grader says that the homeworks B and C grades have been posted. I haven't checked that yet. Do sure, but I got that note this morning. Homework D2 is technically due today, but I did a special thing where I've basically made it the standard late penalties are waived for this homework. So this grace period applies, but it's a standard grace period. It's not the penalized grace period. So you can turn in homework D2 today or up through, I guess, whatever it is, Saturday without a penalty. And so that just gives you a little extra time to work on it. But then there's, then it's the last time you can get it in is that last day, Saturday, and then the solutions will come out. So that way the solutions come out before the midterm. So a couple of things I mentioned last time, and then adding to that, histogram hints are included in the homework assignment. So if you haven't had to generate a lot of histograms, we had some practice on this in the lab. Just want to do that again when it asks you for that histogram when you generate those random variates. Instructions on those, I put it in YouTube, and I've linked to some video instructions as well as some text instructions. Now the latest versions of Microsoft Excel across both Mac and Windows make it very, very easy to generate histograms. Years ago, not that many years ago, it was much easier to generate on Windows than on a Mac. Now that's pretty much they're reached about parity. So it's pretty easy to generate a histogram now. But when you histogram, this is the really important thing, make sure you histogram your random variate and not the random numbers. So if you get a uniform distribution out, a flat histogram across many, many bins, then you're probably histogramming the wrong column in your Excel spreadsheet, assuming you're using Excel to generate these variates. So make sure your histogram has some shape to it. If it looks flat, you might be getting the frequency distribution of the wrong thing. So that's one tip. Other things, submission should be kind of in a document format because we're asking for things like histograms and stuff like that. Do not submit just a spreadsheet full of thousands of numbers. You can submit that as support for your work, but the main submission should be a document that collects like the histogram information and so on. So, I mentioned your docx PDF. If you do have some hand work that you've done in order to generate the random variates, I'm okay with that being captured. It has to be legible and easy to sort of follow from step to step for the grader, but at least should be in a format that, I mean, the biggest thing here is I'm trying to say I don't want just to say, look, I did the homework, here's a spreadsheet of thousands of numbers and that's it. So because at that point the grader can't do anything with that. Really, he has to end up doing a histogram himself or whatever. So you just probably won't get many points, if any, at all for that. So ideally, though, your document, even if it's got sections that have maybe some images of handwritten work in on that, it should sort of flow so that it's very easy to see, okay, for question one, this is my answer, here is my work, this is the results. So it kind of flows in kind of a narrative form. It's a kind of a beginning, middle, and end. And that makes it much easier to grade. And it's much more like what you'd be expected to generate when you write reports when you're in engineering positions there. So otherwise, this Canvas activity F is available, or should be available. I think it's in the midterm unit, which I think you have to unlock by taking that lockdown browser compliance test. But it is a unique ICA in that it samples from all the previous ICAs. It's 3 times as long, but you can take it as many times as you want, and it gets the highest score. So it should be hopefully good midterm practice. And then speaking of midterm practice, Thursday we'll have a midterm review. So I basically grabbed slides from all of the previous slides that I think kind of hit the kind of salient points. And if there are no questions, then I'll just kind of walk through those and see if that generates questions. Otherwise, if you have questions, we can spend the whole time with questions. That's fine. And then next week, Tuesday will be stage 1, which is 80% of your midterm score. That'll be individual. Closed book, closed notes, 2 formula sheets. I say formula, they're just note sheets that are hand produced that can be typed. But I just don't want screen captures of other materials just pasted right in there. There are old versions and solution sets available on Canvas. So again, if you do that lockdown browser compliance test, which you should do this week before next week, so that you're sure that all the stuff, everything's working technically. And if you haven't used lockdown browser since the summer, I think there's been some updates. I think lately with the upgrade of Windows, that there are new versions of Lockdown that have more compatibility. So just make sure that you've got the latest version of Lockdown, and then that will help you make sure of that. So that Lockdown browser compliance test, it's just basically a quiz that says check here, and that just makes sure that it's working. And then there is a workable Canvas exam. It's actually from, I think, 2020 or 2019, or maybe it's 20 from might even be 2022. But it's going to be a very similar format and structure as the exam that you'll take this semester. And then there are paper-based exams that are, again, they're sort of similar. I mean, because I gave them in paper, they asked for slightly different things. They weren't auto-graded, but a lot of those, like for a while, actually switched to Scantron. So they end up being very, very similar in format to the Canvas-based exam. So there's a bunch of practice material in that midterm unit that I hope you take advantage of. And so that's Tuesday for stage one. And then after you do stage one, where you'll get that 90 minutes, you can come here for 75 minutes if you'd like, or you can take it all day. And actually, what I might do is so think about this between now and Thursday. I'm willing to open stage one up Monday, Tuesday, Wednesday, and stage two up Thursday, Friday, and Saturday. And what that would mean that you still have 90 minutes whenever you start it, but you can start it Monday, Tuesday, or Wednesday. So you just have flexibility there. The only downside, if it is a downside of that, is that while the exam is open, I can't answer content questions, because there's always a chance that somebody who took it said, oh, there was this tough question. Can you ask him about this subject, and then ask someone else to ask about that subject, or something like that. So there might be ways to sort of engineer answers out of me that I don't realize I'm getting. So when the exam's open, I can answer sort of administrative questions or whatever, but I can't answer content questions. So if you think you might want to ask me questions Monday, for example, then maybe just Tuesday or even Tuesday, Wednesday is enough. But if you think it just would be nice to have more flexibility, then I'm happy to open up Monday, Tuesday, Wednesday. So I will probably give an iClicker poll on Thursday. So for our lecture F here, so in 2 days here, that basically asks what you would prefer. And if most people prefer, having 3 days availability for each stage, then I'll just adjust the availabilities so that they're Monday, Tuesday, Wednesday. If people would prefer one day, then I'll adjust so that it's only Tuesday and only Thursday. Yep. You don't. If you are happy taking these elsewhere, I will be here. You don't have to be. Yeah. And then so Thursday, same exam, collaborative, open book, open notes. You can come here and work with people here, but you don't have to. Yep. No. So in between stage one and stage two, you don't get information about your score or the correct answers. If I have time, what I'll do is I'll look at the stats for stage one, and I might be able to give aggregate stats. So I can say it looks like questions 15 and 18 were the hardest. No more than 50% of the people got those right, or something like that. And that maybe will help direct your potential attention here, but I won't give anything that'll make it immediately obvious what the right answers are between these two. Any other questions? Yeah. Okay. You mean like I mean, I think that and that's what we'll do today. I think that we are looking for sort of seeing, like, I don't think you need to do a lot. I mean, I don't need to see that you know how to do calculus. The big thing is, like, I need to see that you know how to handle those limits of integration, both within the antiderivative and the stuff that carries over from the previous one. As long as you're sort of showing me that you know how to do that, whether you know how to integrate an exponential, I mean, that'll be obvious in the kind of the answer. Yeah, sure. Um, yeah, I think that. Any other? I had a thought, but I've lost it. Other questions? Okay. Okay. All right, so this is where we've been left. We left off. So we went over all of these, and we've talked about how after the midterm we're going to be taking input models and running them into our sims to get outputs. And so this is an example model where we have failure times, and we need to figure out what's the right distribution for those failure times in our model that includes failure times and a bunch of other stuff. So we drop in an exponential distribution, perhaps on failure times, and then question is, how do you generate exponential random variates? And so there's an exponential probability density function. Has that, it doesn't have to be below 1, just as a reminder, but this one happens to be based on its mean. If you integrate under that, you get CDF, which starts at 0, rises to 1, the cumulative distribution function. And if you have the CDF, then you can generate uniform random numbers on one end, push them in through the inverse of the CDF, and you get an exponential random variate on the output. And so the inverse CDF stretches and squishes the uniform numbers to generate pretty much any random variable that you want. So that's the inverse transform technique. So we say, well, then how do you generate these random numbers? So that's what we talked about last time. So we need a pseudo-random number generator because there is no true source of randomness. And in your average computer, some really fancy computers might have some sort of entropy generators in them, but mostly you're just using arithmetic. And so your real source of randomness is this seed that differs from replication to replication. And then once you give the seed, it's really a question of, do you get an unpredictable uniform sequence out of that? And so that, so in Microsoft Excel, it picks the seed for you from the clock. So every time you reload the same spreadsheet of random numbers in Excel, because the time changes, then you get a different set of random numbers. But in tools like most simulation tools, you actually can yourself edit the seed. And so they have a default seed that they start with, but then you actually have the ability to go in and, like in Arena, change the seed so that replication 1 uses a different seed. And then that way, if somebody else says, hey, I need you to see this replication that starts with seed 4623, you can then just put that seed in, and then you'll get exactly the same execution out that the original person saw. So it's a way you can kind of rewind time and replay a simulated universe by switching these seeds around. And so inside, and this is stuff that it will get more to after the midterm, but I just wanted to sort of convince that there are all of these distributions inside Arena that take this optional argument, which basically say, don't use the default seed, use a different stream that I've provided the seed for. So it's just an example that there are these, so like in Arena, if you want to draw a uniform random number between 0 and 1, you can use unif 0, 1, and normally you don't have a third parameter. But in Arena, you can pass it a stream ID, and that stream ID is the thing you've configured to say, I want this stream to have this random number seed. I want this stream to have this random number seed. And so you can have different distributions drawing from different streams with different seeds. So that also allows you to partition randomness. So you could say, I want my customers to always be identical throughout, so that random number process is always going to be the same across my different models. But my models have their own sources of randomness that I want to be separate from my customer source of randomness. So even though I'm running the same customers through all my models, the models themselves draw their randomness from a different stream so that sort of makes sure you don't corrupt the customer stream. So these are things tricks you can do because you control the randomness inside the computer, which is something you can't do, out in the real world. So, but all of this, the reason it works is because we have uniform random number generators that we can make that are behind all of these things. So it's really important to have good uniform random number generators, which we'll otherwise call just random numbers. And so the two most important properties of pseudo-random numbers are uniformity and independence. So those are two things you should really remember. So we started to talk about the two tests for uniformity, and so I want to pick up there, but then we're also going to talk about tests for independence. So a one particular test for independence. And so let's, and then just in case, make sure everybody sees here that, uniformity, these numbers here are kind of spread evenly between 0 and 1. There's no clumping, there's no range in between 0 and 1 that is overrepresented. Whereas this one has a bunch of numbers that are clumping around 0.2, that are clumping around 0.7, or clumping around 0.1. So there are very few numbers that are, say, near 0.5, for example. So this clumping, if you were to take a histogram of lots and lots and lots of these numbers, it would kind of look more like the Golden Gate Bridge. It would have multiple modes as opposed to just being flat. And that's what you want in a uniform distribution. And then down here for independence, the question is how predictable the number is. So if there's a pattern, then it's not independent. So if I were to give you sample strings on a test, and you can go back and look at some of the old midterms where I've done this, I might, show you a set of bad numbers and I'm going to try to make them obviously bad. And if you look at them and you notice there's a pattern, and that pattern doesn't have to be increasing. It could be that the first number is positive, the next number is negative, the next number is positive, and it always oscillates back and forth. And I may not know the magnitude of that number, but I always know the sign. Well, that's still a violation of independence. So if you can, hopefully look at a string of numbers and say, is there a pattern there? If there's a pattern, it's not independent. If I look at this and I see clumping, so there's like a bunch of numbers like around the same number that keep repeating over and over again, not necessarily next to each other, but somewhere in the sequence. Like this sequence, there's 20 numbers and 15 of them are between 0.8 and 1. Well, in that case, that's a violation of uniformity. You can have both simultaneously. So that's something that hopefully you can sort of look at there. So with that in mind, before I move on to tests of these things, I want to make sure, do we feel confident about these properties, uniformity and independence? Good example, bad example, good example, bad example. Any questions about that? So yeah, this is like, if we think about 20-sided die, this means that there's an equal chance to get any side anytime. This means that knowing how a die roll turned out once doesn't give you any information about how the next die roll is going to turn out. Uniformity and independence. Okay, so tests for uniformity. So the chi-squared test is a review from, I think, 380, and so this is just a chi-squared test applied to a uniform distribution. And as we'll see, for large sample sizes, when your expected number of counts in every bin is 5 or greater, that's fine. But for small sample sizes, when it's impossible to get 5 or greater as an expected number of counts, then we have to turn to a much more what we call a higher powered test called the Kolmogorov-Smirnov test, or the KS test. So we're expected to know how to do both of these tests. You've hopefully, this is again a review from 380, and then you've had some practice at this at your homework. So we're going to do both today. And so the idea here is let's say I give you these numbers, or somebody gives you 30 numbers like this, and they say this is from a random number generator. We don't know if it's good or not. We think that it's probably good. We think that it's probably generating uniform numbers, but we want you to test it. So our hypothesis, our null hypothesis, is that it does draw numbers from a uniform distribution. And we want to see if the chi-squared test will reject that null. So we're going to divide this interval into equal width classes. So on a midterm, I probably will tell you, like, use 4 classes to evaluate these numbers with the chi-squared test. And so 4 in this case could be 5, could be 3, whatever it is. In practice, it's sort of up to you to decide this number. And after the midterm, when we start doing chi-squared tests for other distributions, it will be up to you to grow and shrink this number in order to sort of meet the requirements of the chi-squared test. But for now, let's assume it's fixed. So there's 4. And so I'd say, well, and this is important. You go over the entire expected interval. Like the null interval is from 0 to 1. So some students, when they do this, they look at all the numbers and they find the biggest number and they find the smallest number, and then they use that as an interval and cut it up into 4s. That's not what you want to do. You want to say, what's the null? What am I testing for? I'm testing for it being a uniform distribution between 0 and 1. So I cut 0 and 1 up into 4. So I go from 0 to 0.25, 0.25 to 5, 0.5 to 0.75, 0.75 to 1. Those are my hypothetical four intervals. So it's based on the hypothetical distribution. And then I just count how many of these fall in to how many of these. And so there were 30 numbers here. 3 of them were in this interval, 4 were in this interval, 8 were in this interval, and 15 were in this interval. Well, already my gut tells me this is a bad result. Because what's wrong with this result? What should your gut tell you about this result? What was that? So I'm sorry. Skewed. So what do you mean by that? That's right. Most of the numbers are here. So when we look at this, if this was uniform, without figuring out, without doing the math in our heads to figure like what it should be about, we should know that all of these numbers should be close, but they're not. So 15 is much, much bigger than 3. So it looks like there's too many, actually skewed, there's too many that are at the sort of the higher end of this interval, too many in this interval. Over representation, probably not uniform, but we want to test for that. So we say, well, what would we expect to be in every interval? Well, there are 30 numbers and 4 subintervals. So if it was uniform, on average, we should get 7.5 in every bin on average. So sometimes it's 7, sometimes it's 8, or whatever. So there should be a count of these that, the count on average is going to be around 7.5 in each one of these. And so now we're sort of simultaneously testing all 4 of these to say, does it make sense that these 4 counts could come from a hypothetical count distribution that would have an average of 7.5 in every bin? That's effectively what the chi-squared is doing. So we calculate a test statistic, which sort of calculates an error for every bin. So we're saying that in this bin, we expected 7.5, we got 3. So we're going to square that error. And then you can think of this as normalizing. After the midterm, we're going to actually talk about where this formula comes from. It's not arbitrary. It's not a heuristic. It wasn't just sort of made up. There are super good reasons why it has to be squared up top and not squared in the bottom. Like it looks like the units shouldn't match, but it turns out that this is all on purpose, and there's theory behind it, and that's something we'll talk about after the midterm. But for now, it's just a formula, and you should just think of it as a squared error. So this is the expectation for bin 1, bin 2, bin 3, and bin 4. This is the actual count in bin 1, bin 2, bin 3, and bin 4. So this is like how different it is from the expected in each one of those. It gets squared, and then they kind of all get normalized by the expected value in each one of those bins. And that gives you this test statistic. So what I want you to be building up is an intuition for what test statistics mean. Before, they may have just been numbers, just, uninterpretable numbers. But you should actually, when we publish papers, we publish test statistics because people who read them want to know. So when I look at this, I should be able to say that, okay, for 4 bins, I'm getting a difference of, this is like a difference from my null hypothesis of around 12. So if this was like, it's kind of like if this were 0, then that would mean I am on my null. Like this is the null. But if this were like infinity, then it would be like that's the farthest you could get from the null. We have to reject it. So this is like a distance from the hypothetical distribution. And you can imagine that as you add more bins, you can kind of tolerate a bigger and bigger number because you're going to get more opportunities for there to be error. So you can't just arbitrarily say that 12 is too big. You have to say, well, is 12 too big relative to me having 4 bins that could count error? For 100 bins, 12s might be really, really small. For 1 bin, 12 might be gigantic. And so, so we don't quite know if 12 is too big or not, and that's why we have these tables. And this table basically says that for 4 bins, which has 3 degrees of freedom, and we'll talk about where degrees of freedom come from after the midterm, but basically once you know the count in all 3 bins, you know the count in the 4th bin. So we have to kind of discount the error from the 4th bin. But we're saying that for 4 bins, so remember, you go to 3, you do however many bins minus 1, 3. So for those three degrees of freedom or four bins, then we'd say if we have the significance level of 5%, so we want to falsely reject the uniform distribution only 5% of the time, then our threshold for being too far away is 7.81. Notice that if I get more and more bins, the threshold gets higher, and get less and less bins, the threshold gets lower. And if I get a more stringent, so I want to reject the null hypothesis less, the threshold goes up. And if I want to reject the null hypothesis falsely more, the threshold goes down. So I'm hoping that by the end of the class, not by the midterm, by the end of the class, you'll be able to look at these tables and predict which direction everything should go here. You should be able to say, oh, if I change my alpha, my critical value will go in one way. If I change my degrees of freedom, my critical value will go in another way. So I want you to start building intuition into that. So with here, I will give you this table on a midterm. You don't have to write this table down, but we know that 4 bins, 3 degrees of freedom, 5% error rate, type 1 error, significance level. So my threshold is 7.8 right there. 7.8 is way lower than 11.8. So 11.8 is too big of an error. So we're going to reject the null, which means we're going to reject the hypothesis of uniformity. These numbers with 5% certain, or with 95% certainty, are not uniform. So questions about that? Just a review of the chi-squared. And again, as I mentioned last time, if you ever are given count data in bins and you're asked, does this match a distribution? Whenever you see count data, your head should go chi-squared. It's not always the right test, but 95%, 99% of the time, that's the test you're going to be using. So chi-squared counts. They both start with C. So, okay, is everybody good here? All right, so the question then is what happens when this expected number here is less than 5? Well, it turns out that all of the assumptions that go into why we use this formula right here, why this formula works, is all based on the assumption that this is greater than 5. It basically creates, there's a hidden normal distribution in here, which is what generates all of this stuff here. So these numbers come from the assumption that stuff like this looks like a normal distribution. It all goes back to the central limit theorem. It's crazy thing, it pops up everywhere. And that 5 basically has to do with if that number is not greater than or equal to 5, all of that central limits theorem stuff behind the scenes, machinery, which we will start to peek under the hood and look at after the midterm, so not now, all of that breaks down if this is less than 5, and none of this chi-squared table works. So you cannot use the chi-squared if your expected number of observations is less than 5. So what do? You use the Kolmogorov-Smirnov test, which you've had some experience with. That's why we have 2 tests that are apparently doing the same thing, is that one test is better suited for this special case where you have very little data. And so what do you do with a KS test? And so hopefully you've had practice at this, but you basically take, in this case, let's say I only have 5 numbers, and I sort them. So this blue line here, those are my 5 numbers. I wouldn't give them to you sorted. I might, just if I was being nice, but just to make sure you know how to sort them, I probably wouldn't. And I sort those numbers so that they're rising in value. And I put them into a table like this, where the above them are basically, I create bins around these to sort of say that if I sort a bunch of numbers that are uniformly distributed, then I would expect the first number to be in this bin most of the time. So does that make sense? If they're uniformly distributed and there's 20 numbers, the first number should probably be between 0 and 1/20. Sometimes it'll be greater than that, however, but if they're uniformly distributed and there's 20 of them, the smallest number should hopefully be in this bin between 0 and 0.2. The next highest number will hopefully be in this bin between 0.2 and 0.4, and so on and so forth. And so now we're measuring difference from the bin that we would expect that rank number to be in if they're uniformly distributed. That's what the KS test does. Graphically, that's what we're doing down here, where we have the actual data points are these diamonds, these blue diamonds here, and then so this green line is basically that is the cumulative distribution function for a uniform. That is like, if it really is a uniform distribution, then that is the CDF that it should follow. So by sorting our data, so these are the data values here. And these are the kind of like their ranks here, their ranks divided by n. So you can see here the first number is 0.05. Well, that's 0.05 there. The second number is 0.14. Well, that's 0.14 right here. So it goes up, there's 0.14. And so you can see here, this is its rank divided by n. So this is the first one divided by 5. This is the, 2 divided by 5, 3 divided by 5, 4 divided by 5, and then 5 divided by 5. So when you plot data against their normalized rank, that's something we call the sample cumulative distribution function, the sample CDF. So what the KS test is, it's comparing the sample CDF to the expected CDF. And it's effectively taking differences here. So what we can see is, like, in this case, this point, if we look here, we can say this point, 0.05, it is 0.15 from the upper bound of this interval. It is 0.05 from the lower bound of this interval. So you can see those numbers here, 0.05 and 0.15. And so we look at those and we say that, neither of those are very large, but we're going to keep track of both of those. But if we look to the next one over, this 0.14 is actually below, it's like outside of where we would expect it to be. And how that shows up here is this 0.14, it's maps here to this 0.4 window. And so it's got this 0.26. So 0.4 minus 0.14 gives me this 0.26. That's what we're seeing visualized here. That's effectively the distance from where it should be if it were this green line. So that's the hypothetical green line. So we're seeing quite a bit of deviation there. So by looking across these are effectively capturing the distance from the expected cumulative distribution function. That's how you can visually, if that doesn't work for you, go back to the other interpretation where I gave you, where I say that these bins from the red to the green, from the bottom to the top here, are where uniformly distributed numbers should be if you randomly draw from a uniform distribution. So you can't have some 0.14 is outside of this window, and that's okay, but it can't happen a lot. So what we're going to do is we're going to look through all of these differences. This is the difference between the top and the middle. This is the difference between the middle and the bottom. And we're going to take the maximum of all of these differences. In this case, it's 0.26. And then there is a table. And again, this test statistic here, you can think of that as a difference from the hypothetical distribution, which in this case is the uniform. And so we're saying that for this many degrees of freedom, where in this case, the degrees of freedom are exactly the number of data. So for 5 degrees of freedom, what is the biggest difference from the hypothetical distribution that we can tolerate? And if we look in this table, it's 0.565. So this 0.26 is less than 0.565, so we fail to reject the null. Now, that doesn't mean that these are uniformly distributed. There's only 5 numbers. It might be that we don't have enough data. But the KS test is this really special test that it is very, very sensitive. It will detect very minor deviations from the null, from the uniform distribution, even with a little bit of data. So if it doesn't reject uniformity, it's likely that it is very likely the data actually are uniform. The reason we don't use the KS test for lots of data is it will reject everything. Because it is so sensitive, there will always be deviations from the hypothetical. So that's why we use the chi-squared, because the chi-squared is not as sensitive. So we can use the chi-squared for when we have lots of data, but when we have very little data, we use a high-powered test that's more sensitive, like the KS test. And if it doesn't reject, then these 5 numbers are probably uniform. We have much more confidence in that. So there are questions about that, about the cases when we use the two tests, about how the test works, about the reason for the two tests. That makes sense. Okay. All right. So the other test is for independence. So uh, there are very sophisticated ways to test for independence using so-called autocorrelation tests. If you're interested in autocorrelation tests, in the last lecture, there are slides I didn't go over that go into some details about autocorrelation that I wouldn't test you on. But I do want you to know the term autocorrelation, which characterizes correlations between one sample in a sequence and other samples later in a sequence. So there's ways in which you can analyze how predictable a sequence is from previous portions of the sequence. And you basically just sort of plot a scatter plot of previous data points to future data points, and you see what type of cloud of data you get and fit a regression line. And the slope of that regression line gives you the autocorrelation for whatever distance you chose. So you could say from one sample to a sample 10 samples down the line, what's the correlation between those two samples? And that'll give you the autocorrelation for a 10 sample lag. So those are things you can do to look for autocorrelation, but these tests are sort of more interesting from a data science perspective to sort of look for when things lose correlation in time series. They're less interesting from testing for independence because they will end up fishing a lot because you have to look for autocorrelation at all of these different delays, and eventually you just get a false detection and you have to deal with that. And so they're not really good for testing for independence. They're more good for sort of figuring out how far away two samples have to be before you regain independence. And that's something we'll see after the midterm when we start talking about batching. But so what we do to test for independence are these runs tests. Now, I'm going to show you the runs above and below test. There is also a runs up and down. And years ago, very frequently, I would teach runs above and below, and I would give a paper-based exam where people would do a runs test, and they would then do the runs up and down, showing me that they grabbed like Teresa Wu's old exams, because I think she taught runs up and down, and learned that whole different test and just applied that, and of course got the problem wrong because I needed them to do a runs above and below. But so that's one of the things that if you do happen to be studying from old exams from other professors, make sure you're studying the right thing. So like this is the above and below, not the up and down. So they're related tests, but they're just alternative ways to do a similar test. I do above and below because I think it's easier, but she happened to do up and down. And so for a while, I get wrong answers of people who learned a whole new test that I didn't teach, which was really sort of interesting to me. So let's say I give you 30 data points, just like before. And the question is, are they independent? Is there a pattern here? I don't see a pattern when I look at this, but I want to say like, does it make sense that that there is no pattern here statistically? So what I'm going to do is I'm first going to calculate the mean of all these numbers. Now, I'm not a mean person, so I will likely give you the mean so that you don't have like, because this is just, calculator trap here, right? So if you need the mean, I will probably give it to you. So if you think you need the mean and I didn't give you the mean, but I gave you 30 numbers, that's a hint that maybe you're doing the wrong thing because I just don't think it's useful to have you spend a lot of time taking the mean of 30 numbers. So I will hopefully give you that mean if you need it. But that's how you calculate a mean, add them all up, divide by 30. And then look at each one of those and ask, are you above or below the mean? So I look at this number, 0.18, that is less than 0.67. So I'm going to replace it with a 0. Everything below the mean, I'm going to replace with a 0. And then, so that one's also below the mean. Here's one, 0.86. That's above this 0.67. So I'm going to replace it with a 1. That's above the mean. So I just do that for all 30. So 30 zeros and ones. That's something you will have to do on your own. So then I look at this and I count the number of runs. So basically I'm looking for, and I'm going to diagram this out in just one slide here, is I'm looking for how often do we get repeated numbers. So like 0, 0, that's a run. 1 is a run. Another 0, 0. This 1, 1, 1, 1, 1, 1, that's a run. So how many runs do I have? So in this case, and I'll show you where I got this, I've got 19 runs. I've got 17 above the mean and 13 below the mean. So I also need you to count all the ones and all the zeros. So there's 17 ones, 13 zeros, and 19 runs. Let's see those 19 runs. So this is that sequence, and I just broke it up into those 19 runs. So 0, 0 is a run. A single one is a run. Another 0, 0, 2 ones, a single 0 is a run. This string of ones is a run, and so on. Does everyone see how these are runs? Okay, great. So we count up all of those. Now, the magic here is that if these are independent, if I know how many above the mean and how many below the mean, so this could be a weighted coin. This could be a coin that comes up heads 90% of the time. So knowing the number of above the mean and the number of below the mean allows me to know, how fair this coin is. But a weighted coin, even though it's not uniform, is still independent. So I can figure out that based on the number of above and below, I can figure out a distribution of what to expect for if they were independent. Under the null hypothesis of independence, how many runs should I get given that this is the distribution of above and below? And that's what we get from here. So we don't go into the derivation for this, but so there is, and I would recommend knowing these formulas too, because I feel like I can't give you these formulas because it kind of gives a little too much away. So that's one of those ones that I would recommend having with you. But this basically is saying that if I know the number of above and belows, then I can calculate that if this is independent, then the number of runs should come from a normal distribution that has this mean, which is 1 plus this formula, and this variance, which is this ugly formula. So I just plug them into this. This is a mean of 15.7 and a variance of 6.9. So that's just, under the null, you can find derivations of this, of how you get from here to here. But so once I know that mean and that variance, I can just do a z-score. So I can say, okay, what is the z-score of the number of runs I actually get? Well, that's 19 minus my mean divided by square root. So remember that. You got to take the square root of this to do the z-score. So there's the square root here, and it's around 1.2367. So now this is just a z-test. So now we can just say, okay, if I have a 5% significance level, and this is my test statistic for my z-test. Again, I want to say, how large does this have to be too large? And the thing about these symmetric tests that are positive and negative, we got this one-tail, two-tail issue, is that typically the values we give you are for so-called one-tail tests, but you're going to want a two-tailed result. But because there are, once in a blue moon, you actually do care about a one-tailed test. And we can talk about why that matters again after the midterm. But what you should know now is that if you do this, and I ask you for a 5% significance level, you look for the 2.5% in the one-tailed table. So I go to, even though I want a 5% significance level, that's divided between the two tails. So in any one tail, it's only 2.5%. And that gives me my threshold of 1.96. And that is a number you should memorize, because that number shows up in all throughout statistics, because so many things end up boiling down to normal distributions. And this is the one-tailed threshold for a normal distribution. That's why a confidence interval is twice as big as a standard error, for example. That 2 is the 1.96 rounded up. So 1.96 is our threshold. And so I look here, 1.2 is less than 1.96. So given that, I do not reject the hypothesis of independence. I fail to detect a violation of independence. That doesn't mean that they're not independent, or that doesn't mean that they're independent. It's possible that I didn't gather enough data, but I'd say for 30 observations, and this 19 runs, I have a pretty good confidence that that these are independent, that this is a good enough result for me. Questions about the runs test? Okay. All right. So know the runs test, no KS test, no chi-squared, know how to do the LCG. So I'm not going to go through that example again. It's just plug and chug. We've had a lot of it. And know why you combine two LCGs together to get a combined LCG, which is that you get a much larger period so that you can have two LCGs with that repeat frequently. When you combine them together, then the combined LCG you get back has uniformity, has independence, and it has a very, very long cycle time. That's why we have combined LCGs. So before we go on to doing some calculus examples, any questions on that stuff? We good? Okay. All right. So arbitrary distributions here. So the motivation is you go into a process, an arena. It says, what do you want the timing to be for how long you're seizing this resource? And you can put in an expression here. It has a bunch of standard expressions, triangular, expo, whatever. But sometimes you want a distribution that is not in this list. So how do you write this expression to guarantee that you get the distribution you want out? That's what we're doing. So, if I wanted a uniform, for example, you've seen this in one of your labs at this point. If I wanted uniformly distributed numbers between 2 and 4, I would say I want a uniform number between 0 and 1, multiply it by 2, and add 2. That's the way I get a variate that is uniformly distributed between 2 and 4. So, how do we get these formulas? Where do they come from? And so I've talked about this visually, is that if we have a CDF for a desired distribution, if we invert the CDF, then we have a way to map uniform random numbers to random variates. And this is also called inverse transform sampling. We're sampling from our distribution by using this inverse transform method. So how do we do that? And this is what you practice on homework D2. So we give you a PDF, a probability density function, possibly probably mass function. We'll get to that in a second. And you integrate it to get the cumulative distribution function. This is non-trivial when there's piecewise as parts, as you've seen in the homework, as we'll see here in a second. If possible, so sometimes these are not invertible. So we'll talk about that. But anything I ask you to do, they're going to be invertible. So you find the inverse CDF, which is otherwise known as the quantile function. And so to do that, you just let R equal your CDF, and then you solve for X in terms of R. So again, this may not exist. So the normal distribution is one example, and we have other approaches for that case. But anything I give you, they will exist, and you'll be able to do this. Once you have this inverse CDF or quantile function, you generate a random number between 0 and 1, assuming that your computer gives you one of those, or you use an LCG to do it. And then you take that thing, you run it into your inverse CDF, and the value you get out will hopefully be a random draw from your desired distribution. So let's see an example of that. So this is for just a simple exponential. So here's the probability density function for an exponential. It has two pieces. It's 0 from negative infinity to 0. And it's lambda e to the minus lambda x for everything that is non-negative. So I want to integrate this. So I split it into its two parts. So I say that this first part is everything from negative infinity to x of this 0, which will plop in there. But this second part, this is the thing that you need to, this is what I want you to have down. This is what will be tested on, is like knowing that you can do this, is that to recognize that if x is greater than 0, then to integrate from minus infinity to that x, you have to integrate from minus infinity to 0, and then from 0 to that x. And splitting them up that way allows you to handle these two parts independently and then combine them together afterwards. So in this case here, I'm going to plop in the zeros in the blues. the lambda e to the minus lambda t. I use t as my dummy variable, my nuisance variable here that integrates out, and drop that in there. And then I can plug in, do my antiderivatives, do my limits of integration, combine everything, and there you get our CDF as expected. So there are any questions on that, on how we divided things up? We're not really showing the exciting parts here. Really, the biggest thing for this example is knowing not this part, because it's just going to go to 0, but this part, knowing that you have to go use both limits of integration. You can't just integrate this thing. You have to integrate this thing and then plug in an x minus and then plug in a 0. So remember to do your limits of integration, or to do the antiderivative and then plug in the upper limit minus plug in the lower limit. And then that is how you're going to end up getting this thing here. Because like if you plug in the x, that'll get this part. And then when you plug in the 0, that'll give you a 1 in this part. And then with some rearrangement, then you end up getting this thing out here. So remember your limits of integration. That's the note for this one. We're going to do the harder example next. So any questions about this? Okay. So, and then as a reminder, if you don't remember how to integrate this guy, it's a substitution. So, let u equals minus lambda t and crank away. That's just for those who need the refresher. You can go back and check that out on the slide. So now that we have this inverse, or this CDF, we need to find the inverse CDF. That's pretty easy for this one. We know that all of the values from 0 to infinity map to values from 0 to 1. So that's what we got. So we know that the inverse is going to be the reverse of that. All the values from 0 to 1 are going to map to 0 to infinity. So I'm going to set R equal to that bottom part, the only part that actually has any support. And I'm going to solve for x. So I go down through here and I get, this is my inverse CDF after some rearrangement, taking some natural logs, et cetera, et cetera. There you go. Now, a fun thing about this is that you will see inverse transform, or you will see exponential random variate generators implemented in code, like in Arena, if you look at their code, not with 1 minus R, but with R. And that's because if R is uniformly distributed between 0 and 1, so is 1 minus R. So an optimization is to just drop the extra arithmetic, because you might be drawing a million random variables. So why do extra arithmetic for every one of them? And just say, well, let's just replace it with uniformly distributed there. So that's a little trick, and that's where that comes from. All right, so any questions about how we got here? So then if I wanted to generate a histogram, I just generate a bunch of numbers between 0 and 1, plug them into here, and then take a histogram of the result, and it should hopefully have that slope shape to it. Okay. All right, so this is what that histogram would look like. So I take generate a bunch of numbers from 0 and 1, I plug it in, I generate a histogram. This is the expected value, this is the actual bins that I get out of my histogram. In Arena, if I want to plug that in as an expression, RA is a shortcut in Arena for giving you a random number between 0 and 1. That's equivalent to unif 0, 1, as I showed you earlier. And ln is natural log in Arena, and multiply it by minus 1/2. And that is equivalent to just putting this in Arena, which is give me an exponential random variate with a mean of 1/2. So that's, and if I generate a bunch of those and I take the histogram, that's what I get. Okay, so let's look at a more complicated example, more like your homework. So in this case, I've given that the density of a triangular distribution. I would like to generate numbers with a triangular shape, with a triangular distribution. So that's my density. This is the CDF that I would like to integrate under this to get this. So how do I do that? Well, I'm going to take these 4 parts and I'm going to break them down here in this kind of triangular form here, just coincidentally. And so this first row is for everything from minus infinity to for this first breakpoint. This second row includes the contribution from the blue line plus the contribution from the magenta line here. So I've got the blue from negative infinity to A, that's that first breakpoint. and then from A to X, where X is in between A and C. And I just do that for in the third row, I get this plus the little bit of contribution from the green. And then finally for the fourth one, this plus all of this plus all of this plus the little bit of contribution from the X that's left over. Are there any questions about how I've set this up? Where I look at where X is and then ask what are all the X's before it and make sure those are included. So X shows up in the limit of integration in the last one, on the last term, but in all of the other terms that are underneath here, then the limits of integration are constant. Okay. So I can now plug in, I take this 0 and I plug it in everywhere. I can take this magenta term and plug it in everywhere. I can take the green one and plug it in everywhere, and then the red one and plug it in everywhere. So if I do all of that, I end up with this thing. So I got these 4 ugly pieces here. The nice thing is that if once you solve for this guy, if you plug in at C, you're going to get this term here, basically. So this whole thing collapses on itself as a telescope. So you really only have to do the calculus for the things on the edge, because this part will be the previous part evaluated at that point there. So you just, once you get this right, plug in C, and then that will be this whole purple term. So you don't have to do anything new here. Then you just do this one. Once you get this right, plug in B for this whole thing, and then that will give you what goes here, and so on. So we do all of that. So this is after our antiderivatives and our limits of integration. We get this stuff, which have all of the parameters here. And now we can simplify because we notice some things that we can combine together, and we get a CDF. And it's a nice CDF that starts at 0 and ends at 1, just like it should. We do a sanity check. If we plug in a B here, then that B, that's going to give me a 0 in the top. It's going to give me non-zero in the bottom. So 1 minus 0 gives me 1. So as expected, this edge does touch 1 like it's supposed to. And if I plug in an A over here, then this portion goes to 0, which goes to 0. So everything smoothly rises from 0 up to 1 as expected. So any questions about that triangular distribution? How we got the CDF there? Okay. So that's was the first tricky part, was getting those limits and everything correct. Then the next part is inverting this thing, because it's got all these pieces and you have to be careful about how you invert them. And some of those pieces are non-invertible, like the squares. So you have to figure out which square root to take. So I look at this thing and I say, all right, the support for this distribution are the pieces of the CDF that are non-constant. So I only care about these middle pieces here. Or in other words, in the density, it's the portion, it's the ranges, it's the range. But so the range of this thing is where the density is non-zero. So it's only the middle 2 pieces. So equivalently, it's where the CDF is non-constant. So only these middle pieces here. So I know that this piece represents this X range. This piece represents this Y range. If I plug this A into here and this C into here, that will give me the R range that this piece corresponds to. If I plug this C into here and this B into here, that will give me the R range that this corresponds to. So that's what I've done here, is I've plugged the whole range from A to C into this thing, and I've plugged the whole range from C to B into this thing. And that tells me that the R ranges for my inverse CDF. So the sort of domain split in my inverse CDF is going to be from 0 to this ratio. And then that'll be for this portion, for the top portion. And then the other side here is going to correspond to an R range from that ratio to 1. So those limits will be important here in a second. Are there questions about what I mean by this, about R and X ranges and how they map? Okay, so for this inverse CDF down here, and I'm just summarizing this in a more compact way, I just flip that. So I'm saying if this CDF maps these X's to these R ranges, then the inverse CDF does the reverse. It's going to map these R ranges to those X ranges. So that's what I've said here. So if I draw a random number from 0 to this range, it should give me an X value out between A and C. If I draw a random number between this and 1, it should give me an X value between C and B. That's what I need to know when I do these inversions. And so I'm going to set R equal to the top for this X range and R equal to the bottom for this X range. And I'm going to do the inversion. So I just do that compactly in these cases here. So if I invert this guy, so I'm just kind of doing the arithmetic here. This is one step of the arithmetic. Likewise, in this one, I said R equal to this and do a little cross multiplication. This is another step in that arithmetic. And then I finally am able to solve for X here. And so I'm able to say X is equal to this blue line for this R range. Now, that's where that mapping came into play. I know that X from A to C corresponds for R from 0 to that ratio. So there's where that ratio comes up. Likewise, X from C to B corresponds to R from that ratio to 1. Now, the tricky thing here is because there were squares involved, I had to take square roots. So I had to choose the plus and the minus here to ensure that for this R range, I got the right X range. So I want to know that when I plug an R into this thing, when my R is between these values, I want to make sure my X is greater than A. So that's why it's A plus. When my R is between these values, I want to make sure my X is less than B, which is why it's B minus. So that's how I choose the plus and minus. It's not always plus, it's not always minus. It depends on whatever X is supposed to be. So are there questions about that? It's like the hardest thing we have to do. Okay. So I can do my histogram just like before. I take a bunch of R values, plug them into that formula. I get a triangular distribution out, which is great. Fortunately, in Arena, if you need a triangular distribution, they've already done all this work for you. You just do tria or tria with your min, with your max, and your mode. Alternatively, you can implement that ugly thing. This is what it would look like. You can create this assignment block. You can assign a value, you can assign a random number to a value R, and then you can implement this ugly piecewise expression where it basically checks to see if R is in the lower range and it uses the lower formula, or if it's in the upper range, it uses the upper formula. So it's pretty ugly, but conceivably, if you had something that wasn't triangular, that was your own special distribution, there are ways in which you can implement these sorts of things. But fortunately, for most of the common ones, that vocabulary that I said that you build up originally, then the Rockwell or whoever the simulation providers are have also know that vocabulary, and they've already built most of those things for you, so you don't have to do this. But occasionally you do, and this is an example of how you might do that. Okay, so there it is zoomed in. Sorry, I should have done that, but it's a mess. Not expecting you to be able to do this for the midterm, just showing you that you can implement the thing that we just derived in Arena if you really wanted to, but fortunately you don't have to for the triangular. So for most distributions like exponential, uniform, Weibull, or whatever, not only are they already implemented in simulation tools, but if you absolutely needed the inverse CDF, then you can just go to Wikipedia and look down the left hand or the right hand side, and it'll have an info sheet on that distribution, and that will include the quantile function or the inverse CDF. They might use both words. You should know both words. Quantile function is a synonym for inverse CDF. And so that's what I'm saying up here. This is just, if you look up the exponential, it will give you the quantile function. If you look up the triangular, it will give you the quantile function. So for these common ones, somebody's already done the work. You just grab that formula, and then you can dump that into your MATLAB or whatever, plug in uniform random numbers, and you will sample from that. That is how you sample for complex distributions in Excel, for example. You just implement that in Excel and you can get a triangular distribution, even if Excel doesn't have a triangular distribution, which I think it actually does. But there are weirder distributions, like Excel, I don't think has a Weibull. But so if you wanted to generate Weibull data in Excel, you just implement that in Excel and plug in uniform random numbers for there. Questions on any of that? Does that make sense? Okay, so some closing then comments then. So I want to make sure you know that you also can do this with a discrete random variable. So I can give you a probability mass function. You can calculate the CDF just by summing these things up together. And then you can basically invert that discrete CDF. So we're just going to draw random numbers and bring them in this side here. That's equivalent to me flipping this thing over and then just plugging in the random numbers now at my new R axis, which is just the folded over version. So here's my CDF, there's my inverse CDF, and then I can just take a random draw from 0 to 1, and that gives me my outcome. So we've already seen this, the random dart transformation, but this is just the same inverse CDF that we just did in calculus. So, but in the discrete variable, the CDF gives boundaries as opposed to pointwise maps for mapping ranges or groups of the uniform distribution into discrete outcomes. So that's how that works there. So we can see the boundaries here. Anything from 0 to 0.2 will go to outcome 1. Anything from 0.2 to 0.7 will go to outcome 2. Anything from 0.7 to 1 will go to outcome 3. So know how to do that. So know that if I were to give you a PMF and then give you a bunch of random numbers, know that be able to draw outcomes according to this using these boundaries. And there are some examples of that you can see on sample midterms. Now, when you're doing this for real, there is fortunately in Arena a function called disk, where you just load the inverse CDF into disk. And that's why you load the probability first and then the outcome second. So this is loading the inverse CDF into disk, and it will then it will do this for you. But you have to calculate the CDF for it. So that's something that in Arena, you might think that you'd load the probability mass function into disk. But like I said, when you do a lot of stochastic modeling, your mind moves away from the density and mass functions and into CDFs. So we think in CDFs in simulation and in stochastic modeling. And so it's just very natural to supply the CDF and not the probability mass function. So remember that. If you try to put a probability mass function in here, it will give you an error because the odd numbered arguments won't be monotonically increasing necessarily. So that's an example for this one here. I can log in 0.2, 0.7, and 1 corresponding to outcomes 1, 2, and 3. So it's good to know this this syntax as well. So that would be something that if I was going to ask you anything about Arena, it would be something like being able to read this line and know that it is encoding an inverse CDF. Okay. So I've mentioned this already, that if you plot a data point against its rank, its normalized rank in a sorted list, that is the so-called sample or empirical CDF. And so if you were to think about it, you could create a probability density function where every outcome of your sample data occurs with probability 1 over n. And so then the CDF is just sort of that basically. So that's where this sample CDF comes from. So with that, the idea here that what Arena is doing is this inverse transform technique where if you draw a bunch of values, it's going to give you just those values out. So that's the thing about like if you were to gather data, if you use disk based on that data, then you are telling Arena you only want the outcomes that you have in your data. So I have these 5 outcomes. Now, it might be that actually I took a subset of my real data. There are things in between these outcomes that I just didn't gather data on. And I would like Arena to give me a more continuous range that somehow still manages, that somehow still gets the statistics of the points that I captured right. And Arena gives you the ability to do that. You can basically turn disk into, you just swap out the disk and replace it with something called cont for continuous. And it basically then generates data so that it will fill in the blanks between your samples so that, like before, remember this here, I only got these outcomes, outcome here, here, these whatever 5 outcomes, 1, 2, 3, 4, 5 outcomes. What Quant does is it connects these, creating a CDF that is continuous, but has the same corners. So sometimes that's useful when you take a bunch of data and you want a continuous spread of data, but you don't have a good distribution for it that's from our table. And so you just quickly say, I'm going to take the data as they are, and I'm going to, instead of implementing it with disk and Arena, I'm going to drop in a cont, and then it will then fill in the gaps in between the variables. So that's the other thing. I kind of just want you to know the difference between disk and cont. It just, whether it interpolates or whether it just has these stair-step functions. And then the rest of this is just sort of special case stuff that that I don't necessarily need you to know, in great detail. There are some distributions where there are analytical inverse transforms that you can get out. I just show this example that you can look at separately to see how that might work, but I'm not expecting you to know this. And then the other things that I just want you to sort of know that happens that exist is that there are some CDFs that are not invertible. And one of the unfortunate ones is the normal distribution. We use that so much, but we can't actually invert the normal CDF. It's not in a form that's analytically invertible. So what people have done is they've done things like approximate it. They create functions that look like the inverse transformation, so they fit it like close in a data. Like if you invert this, it's going to look like a bell curve. And then people use that as a surrogate. That's one way people do it. And then there's a bunch of other little clever things that people do. Like they've noticed that the chi-squared distribution is actually the sum of normals, but the chi-squared distribution is also itself an exponential. So there's tricks where you can draw an exponential and a uniform and combine them in a fancy way to get 2 normals out. I'm not expecting you to know that, but I just want you to know that there are these cool tricks that you can use to sample from normals, even though we can't actually invert a normal CDF. So if that question comes up where you're like, well, I don't know, he said that there's some CDFs we can't invert, how do we draw from them? People have figured out all sorts of cool tricks to do that, and that's sort of one example there. So I'll sort of close on this kind of takeaway. This is more advanced stuff. The most important thing that I want you to get out of this lecture and to know for the midterm is how to do an inverse transform on a relatively basic invertible CDF, and know how to do it for both discrete and continuous. So know that how you can sort of use the logic of the inverse transform as applied to the continuous, generalized to the discrete as well. And the rest of this is just kind of bonus. And so don't worry too much about that, except know that if you need to implement a disk in Arena, a discrete random variable in Arena, there is this disk command that just takes, remember, the inverse CDF. The odd arguments are probabilities, the even arguments are outcomes. All right, so that's all I've got for you. And I'm happy to take questions after. Let me give you one poll. And this poll is, I'll do a short answer, and it's and the question is, are you required to come to class next week for any of the midterms? That's the question. Yes or no? Are you required to be here next week during the midterms? And then as you leave, think about whether you want me to open the midterms up for 3 days each phase or just one. Mhm. Hmm. Yeah, let me just stop this here.